Hello friends, welcome to my home, and this is the video that we finally get to the concept that we've been building towards this whole time. So up until now we've been talking, basically we've been using these sums to approximate a certain thing. In one situation we were approximating the distance a car traveled. Another we were approximating the area between a road and river. And we found a couple ways of making better approximations, and this is going to be the best way, but only if we have a certain amount of knowledge. So, the situation as is, our summary. If we have just data, we've got basically three options. There's a fourth, but I'm not going to get into it because there's no reason to do so. We have left sums, we have right sums, and trapezoids is just the best we can do because it's based on the data we have. We can't go out and get more data ourselves. So, but what if we knew more? What if we knew a little bit more about the situation instead of discrete chunks of it? Here's an example. What if we had a function, a well-defined function at every point, instead of just discrete or just data like we had earlier? Here's a function, looks like some kind of quadratic. Well, one of the examples is that we can make any partition we want. If we were interested from 0 to 5, well, we have to have 0 and we have to have 5. But we could do it, 1, 2, 3, 4, 5. We could partition at 0, 1, and then 4, 4.1, 4.2, 4.3, 4.4. If we wanted to do that, we could partition at every 10th. We could partition at every 100th, right? In addition, so let's just do a quick partition where it's just every 1. A nice even partition. They're easier to work with. I think you might have noticed so far. In addition to that, we're not confined to using the left side or the right side. We can use any point in the partitions that we want. This comes in your book as MRAM, which stands for the midpoint. Rectangular area method. So on this partition, instead of using this side or instead of using this side, we could just go right in the middle. Draw a rectangle there. Why not? Doesn't get into the problems, or doesn't get as much into the problems of LRAM versus RRAM, which we can get into later when we're talking about just applications here. But yeah, you can use midpoint. Use any point in the partition we want. So now let's think about it. We're doing an approximation, and I'm just going to draw in, I don't know, a left-hand side. So we'll have our partition from earlier, just partitioned on the ones, right? And we're going to do a left-hand approximation. Why not? So we've got this, then we got this, then we got this, and this, and this. And this is our approximation for, in this case, like I haven't given a situation, so we're just approximating the area under a curve. You're going to be seeing this phrase a lot, the area under a curve, so get used to seeing it. So we made a partition to approximate the area under this curve from 0 to 5, right? Let's do it again. 0 to 5, except instead of doing it that, let's do just more. And so we'll still use the left-hand sum, but and we ask ourselves this, selves, after filling this out, which partition do you think better approximates the area under the curve? This one or this one? Well, it seems like this one's kind of our answer, right? The one with more seems to be better. And for a lot of functions, this is the case. More is better. To use our summation notation, if we had a partition with 5 elements, so the sum from I equals 1 to 5, with our, again, left sum here, this is markedly worse in that case than our partition with 10 elements, or with 10 subintervals, right? Okay, well, if we follow that logic, the more subintervals we add, the better it is. Well, there must be, and especially since we know, like, with our function earlier, right? This is some well-defined area, we just don't know what it is. So if adding to the partition and making better, there's probably a best, the true area under this curve, that you get closer to as you add more and more rectangles. Well, that sounds like a limit. Hey, we're back in talking about limits. Suddenly, since we're talking about limits, this falls under calculus again. This is going to be our particular limit, and you want to kind of internalize this. So our approximation so close that is the real thing is going to be the limit as the number of subintervals increases without bound of our sum over these subintervals. I switched it to the right. It doesn't actually matter. It should be the same either way. But yeah, so this is kind of the gold standard, right? For all the things we've been doing earlier, it's been approximation, approximation, approximation. The best approximation must be made with infinite rectangles. And the only way to get to kind of an infinite rectangles, infinitesimal distance, is our limit. Okay, this has this particular term. We call this the definite integral. So I'm going to throw some words at you. For some function f defined on some interval a, b. For right now, we're only defining this on closed intervals. With a partition of size n, the limit, as n increases without bound, of our Riemann sum is called the definite integral of f from a to b, right? We're going to be working with definite integrals. This is, the definite part is important. We'll get what it contrasts to later. Notation-wise, so how are we going to write this? The sigma that stands for sum, this fancy angly thing, that's a Greek s. When we move to the limit, to the definite integral, it is changed to this funky symbol, which is just a normal s that's been stretched out. So it's a long s. This is the integral symbol. And the delta from our sum, this delta, which is a Greek d, is changed to a normal d. It's actually usually italics d, but I can't distinguish italics when you're writing it. So, when we want to say the definite integral of f from a to b, we write it this way. This is the definite integral from the starting to the finishing. So you always go from bottom to top. So from a to b of f of x dx. And this is how we write the definite interval. This can mean, when you see this, the meaning that you want to come to your head is area under f from a to b, right? But this is how we write the integral from a to b of f of x dx. The dx is important. Now, how do we find the definite integral now that we've introduced it? Well, there's the real way, which is too scary for you. And by you, I mean for AB students. because actually generating that limit with limit notations requires a lot of knowledge about series, and we're just not going to touch series at all. We don't have time for it. If this were a BC class, you'd go deep into series and do a lot of series, so you can do it the real, and by real I mean hard way. But in this case, we have no time for it, and we're just going to hand wave it. And so it's like, oh, we're not doing it that way. Okay, so if we're not doing it the real way, how do we do it? One way is using background knowledge and tricks. We talked about area under the curve. Well, there's plenty of areas that you know how to find already, and we'll get to that in the next lesson. And then there's the way you're going to be using the most often, which I'm not going to tell you. It's a secret, but just a secret for now. Anyways, that's what we're building towards, the definite integral. Thanks for stopping by.